This video is a quick introduction to spherical and cylindrical coordinates. Here we have the x positive axis, the y positive axis, and the z positive axis. From the origin, we're measuring out a distance r along the x positive axis. Draw a circle of radius r in the xy plane. Pick a point on that circle. The line segment connecting the origin and that point will create an angle theta with the x positive axis. That point has an x coordinate x0, a y coordinate y0. Since the point is picked in the xy plane, the z coordinate is 0. Allow the z-coordinate to take any value you like. Here we've drawn it such that the z-coordinate is taken to be positive. This point P then has coordinates x0, y0, z0. These are rectangular coordinates. However, the point was produced by picking an r and a theta and a z0. Thus, the point can also be described using cylindrical coordinates, r, theta, z. Now, let's look at how to convert between rectangular coordinates and cylindrical coordinates, and vice versa. To do that, let's draw in a right triangle. This right triangle has a base measuring x0, a second leg measuring y0, a hypotenuse of r, and one acute angle measuring theta. Here is that same right triangle drawn in the xy plane. The base of x, a height of y, a hypotenuse of r, and an angle theta. Let's look at this right triangle and note that we can write down r as the radical of x squared plus y squared, thanks to the Pythagorean theorem. We can note that tangent of theta is, by standard definition, y over x, or opposite over adjacent. Equally, we can think of definitions for cosine of theta as adjacent over hypotenuse and then solve for x. Likewise, sine of theta would be opposite over hypotenuse and then solve for y. These two sets of identities are what allow us to convert between cylindrical and Cartesian coordinates. Cartesian coordinates is just another name for rectangular coordinates. To understand what we have here, think of being presented with rectangular coordinates r, theta, z. Then we can plug into these equations to produce x's and y's. And z is simply z. On the other hand, if we're presented with an x, y, and z for the coordinates, we plug into these two equations in order to produce the r, theta, and z of cylindrical coordinates. Nice. Let's think back for a second to rectangular coordinates. That if we take an equation like x equals c, this is only placing a restriction on the x. We're free to vary y and z as we please. We get a plane which is parallel to the yz plane. Likewise, the middle picture is another vertical plane, which is parallel to the xz coordinate plane, and its equation is given by y equals c. Likewise, the right plane, which is horizontal, has z fixed to some constant, and we're free to move x's and y's. In cylindrical coordinates, we had earlier that r was set equal to a radical. As such, we're going to make the assumption that r will always be non-negative. r is measuring the distance to the z-axis. So all points of a fixed distance from the z-axis would form a cylinder. If r is non-negative and we fix theta, if we take the equation theta as a constant, we're free to move in this direction away from the z-axis, but only in one direction, in the positive direction, not in the negative direction. Hence, theta equals c is a half plane. Nice. That was cylindrical coordinates. We're now ready to move on to spherical coordinates. In spherical coordinates, we have variables rho, theta, and phi. Let's begin. Like before, we have the x positive, the y positive, and the z positive axes. From the origin, measure along the x-axis an amount rho. Draw a circle in the xy plane of radius rho. Draw a second circle of radius rho in the xz plane. In fact, think of all points exactly rho from the origin and visualize a sphere. For convenience, I will refer to this sphere as the Earth. Then the circle in the xy plane, I can refer to that as the equator. Pick a point on the equator like before. That point will sit rho away from the origin, and that point will determine an angle theta as before. Watch that point travel along the Earth until it reaches the North Pole in the shortest possible path. Trace that path. Pick a point on that path. That point will sit rho away from the origin. That point will sit z above the xy plane. Dropping a perpendicular from the point down to the xy plane, we'll pick a point in the xy plane that is exactly a distance r from the origin. R is measuring the distance of point P to the z-axis, also measured with respect to the z-axis, in particular z positive, is the angle phi. From the origin to the point P, that line segment with the z positive axis forms an angle phi. In this picture, we already have an r, a theta, and a z. Those are exactly cylindrical coordinates. We know that given cylindrical coordinates, we can convert into rectangular coordinates. In this picture, we're able to identify a point P by specifying a rho, a theta, and a phi. These are exactly the variables of spherical coordinates. Like before, we want to address how to convert between coordinate systems. To do so, we again draw a right triangle. In our picture of the sphere, we have a right triangle. We've reproduced that right triangle. We've also drawn in a vertical line. This represents the z-axis, so that the hypotenuse of this right triangle is forming an angle phi with the z-axis. This then allows us to identify one of the acute angles in the right triangle. Like before, let's state elementary trig definitions for this right triangle. Cosine of phi is adjacent over hypotenuse. Sine of phi is opposite over hypotenuse. Solve these for z and r, and come up with z equals rho cosine phi, r equals rho sine phi. Nice. We'll need both sets. The bottom set, let's go back and state how to convert from cylindrical coordinates into rectangular coordinates. And then note that we can swap out our expression of r for rho and phi, and thus we have established how we can go from spherical coordinates in rho, phi, and theta and produce x's, y's, and z's. What about the other way around? Let's write down 3 more equations. This top equation is simply the equation of a sphere of radius rho. The second equation is borrowed from cylindrical coordinates. The third equation is just a restatement of what we observed in our right triangle, where the denominator rho has been solved for in the top equation. Nice. These 2 sets of equations allow us to convert from rectangular x's, y's, and z's to spherical rho, theta, phi. Likewise, the bottom set allows us to convert from spherical rho, phi, theta into rectangular x's, y's, and z's. Beautiful. One last thing. We have 3 pictures. These 3 pictures correspond with the 3 variables of spherical coordinates set equal to a constant. The first is a picture of a sphere. Rho equals a constant. The middle picture is a half plane, as we saw before. Theta equals some constant. The third picture is phi set equal to a constant. This picture is a picture of a half cone. This half cone is drawn above the xy plane. It is a half cone, that means it's missing a portion. The portion that's missing would be sketched below the xy plane. If you have a half cone drawn below the xy plane that corresponds with phi equal to a constant, that phi would be an obtuse angle. Here pictured, this phi corresponds with a acute angle. Beautiful. That was a quick introduction to spherical and cylindrical coordinates.